In this lecture, we're going to look at what seems to be the most basic case we can think of, and that's the free particle. And the free particle is the case when we have the potentials being zero everywhere for all time. That's why it's called free, because it's not interacting with anything. There's no potential. In that case, the Schrodinger equation takes the following form we see here. And we want to look at the solutions of this and see what the properties of that are. It turns out it's actually there's a lot going on with the free particle case. And there's a lot to discuss about it. So we're going to begin, as we've shown before, we'll assume this isn't a definite state. And if that's the case, we know that the left-hand side of this equation is just equal to E psi. That's how we kind of constructed that in the first place from the wave equation. And E is going to be a constant here. And this particular equation, as written here, has the simple solution e to the minus iet over h bar. However, we know this is not the full solution because we have the right-hand side of the equation. And if we just take the second derivative, we see that vanishes because this is independent of x. So we want to construct the full solution, including the spatial dependence. It's not hard to do. You just have to look at that equation and inspect it. But let's try the following form. And again, just momentarily, notice that if we're going to take two derivatives of psi, and there's a minus sign coming out, if we're talking about exponentials, that will not work. Or we could use sines and cosines. That would work because two derivatives of cosine is minus cosine, and same with sine. Or we can use complex exponentials. So whenever we have a minus sign with a second derivative, it's telling us complex exponentials are a form of the solution, or is a possible solution. So we'll look at the general solution, and again, we'll keep the time dependence here. That part is here. So these are the same, e to the minus iet over h bar, and same here. But let's just insert a factor b and see what we get by inserting into the formula. We get E psi again, which is what this is equal to, is b squared h bar squared over 2m psi. And we see we'll solve this equation if b is equal to plus or minus square root of 2me over h bar squared. So we can write our solution of this form, of the free particle. Again, we have to consider both plus e to the plus I and e to the minus I to have a completely general solution. And again, here we're going to rewrite it in terms of k, which is square root of 2me over h bar squared. And this form is really a general form. And k is what we call the wave number. And it's equal to 2 pi over the wavelength, if you like. And we also can rewrite the time dependence by going back to the form for energy is equal to hf, the frequency, which is equal to h bar omega, the angular frequency. And in that case, we come back to this form here, which is often the first form you see when you look at solutions of Schrodinger's equation, kx minus omega t. And we can, again, we can just express it different ways. Here's another way to express it by using E is equal to h bar squared k squared over 2m, which results from the formula up above, just by solving that for k, or E actually, where b squared is equal to k squared, and factoring out a k here, we get this form as well. Now, the reason to write it in this form is for the following, because whenever we have a function of the form of x, the argument is x minus vt, that meaning that wherever we are, whatever type of mathematical expression is, x minus vt is always there where v is a constant. This represents a waveform which takes the shape of f, whatever f could be, any kind of random shape there, and it will travel in the positive x direction with speed v. So just as a quick example, if I say here's some weird waveform, I can call this f. Okay, so this is f. But what happens here is that if it's equal to that, this moves off to the right at some speed v. And again, if I want to make it go to the left, I just has to be x plus vt. That should be clear just by looking at it and playing around with it. You should see that. But since we have x to the minus h bar k over 2mt and x plus, we just said, that represents that this solution has two types of waves in it, one traveling to the right, one traveling to the left, with the speed of h bar k over 2m, which we can revert back in terms of the energy as the square root of e over 2m, using the relation we had before. So that's the speed of this wave in this format here. Now, here's an issue, is that if this is going to represent a particle of energy E, a free particle, we know from classical physics that the energy is equal to E comes from the kinetic energy. It's all kinetic, right, if there's no potential. We solve that, we get that v, the classical speed, is square root of 2e over m, which is twice, if we factor out that 2, we see it's twice the speed of the wave represented by the wave function. So this indicates we have an issue here if we're going to think of this free particle solution as representing a classical particle moving at some speed, meaning it has a different energy, different kinetic energy in that way. So we see there's a problem, and we're going to return to this in a later lecture just because there's plenty to say about that issue. Okay, let's move on, and we'll talk about another fundamental problem with the free particle state. Remember that the wave function gives us the probability density. Psi star psi gives us p of x of t. And since that's a probability density, and we want our probabilities to be normalized, when we integrate over all space, again, we're talking about only one dimension here, this has to equal 1, the normalization of probability, as we said. Well, let's look at what psi star psi is in this particular case. And I'm going to use this form just because it's easier to write. E to the minus I kx minus omega t, and e to the I kx plus omega t. So we notice here that the psi star just flips the sign of I. So we have a e to the minus I and b e to the I. That's for the psi star. And here a e I and b e to the minus I. So that's how we write that form. And when we multiply this out, notice now carefully that when we take a on a here, we get a squared plus e to the minus I kx minus omega t times e to the I kx minus omega t. Well, e to the minus I something times e to the plus I something is equal to 1. Same with b. So we simply get a squared plus b squared plus the cross term when a here, which takes this form here. Remember, and note carefully, you want to carry this out if it's not clear, the time dependence cancels there. And we can rewrite this term here by using the Euler relation as 2ab cosine kx, which we don't particularly care in this case, because really what we want to show is that if we now try to normalize this or integrate it over all space, we should get 1. However, notice this integral. A squared is just a constant. It's a normalization constant. It could be complex, but it would be a star a, so it's just a complex constant. So dx from minus infinity to infinity is infinity. What it means is that this free particle solution is not normalizable, and it's an unphysical state. We cannot have a particle, at least within quantum mechanics, that's absolutely free and has a definite energy. It's just not allowed. So that tells us this is a problem. But it doesn't, because it's unphysical, doesn't mean it's of no use. And it turns out it's actually of extreme use. We use it a lot. And the reason is the following, because in quantum mechanics, we can always take solutions, just like in any wave equation, linear wave equation, I should say. We can take two solutions, add them together, and get a third solution, what's called linear superposition. And since we're dealing with a wave equation here, the Schrödinger equation, we can take two solutions of different energies, add them together, and that's also a solution of the wave equation. So if we do this in the right way, by combining what we call taking a linear combination or linear superposition, if you will, of free particle states, you can actually generate realistic solutions. For example, one that looks like a wave packet. That's non-zero in some region and zero outside. We'll look at that specific example later. And in general, now, and again, we're talking about free particle states of different energy, or we could just think of it as different k, because k is directly proportional to E. So a general solution now, because of k can be a continuous variable here, we get that we can just separate it in this way. We add each term. Again, k now is allowed to go to negative values here, so k is going from minus infinity to infinity. And we can, this term phi here just tells us how much amplitude there is for each particular energy state. But it's a continuum. And then we integrate over all k, and this will allow us to construct non-trivial wave functions psi x of t. And again, this can be normalized if psi k's are chosen appropriately. It's no problem there. Now, as we go forward, what we want to do is see how we can explicitly construct solutions in this manner, and this is what's called Fourier analysis, and also to come back to the problem we talked about with the speed of the wave. We'll do that in a later lecture.